Welcome to True Projects. In this video, we are going to explain about the project title Enhancing Well-being, a machine learning approach to detecting stress in IT professionals via image analysis, video analysis, and audio feature analysis. Introduction. The project focuses on employing deep learning techniques to identify stress levels in IT professionals. By leveraging deep learning methods, the project aims to analyze various types of data, including images, videos, and audio features, to accurately detect stress levels among IT professionals. The primary objective of the project is to achieve precise detection of stress in IT professionals to enable timely support and interventions. Stress can have significant diverse effects on individuals' well-being and productivity, particularly in high-pressure environments such as the IT industry. By accurately identifying stress levels, the project seeks to provide timely assistance and interventions, thereby mitigating the negative impact of stress on the well-being of IT professionals. Traditional methods for detecting stress, such as self-reporting and physiological measurements like heart rate variability and skin conductance, have inherent limitations. These methods are often subjective, relying on individuals' perceptions or active participation, and may not provide real-time insights into stress levels. As a result, there is a need for alternative approaches such as deep learning techniques to overcome these limitations and improve the accuracy and efficiency of stress detection. In this project, deep learning models are employed to analyze visual and auditory cues associated with stress. These models are trained to extract features from images, videos, and audio signals, enabling precise real-time feedback on stress levels. By leveraging deep learning techniques such as convolutional neural networks, CNNs, for image and audio analysis, the project eliminates the need for self-reporting or invasive measurements, providing a more efficient and accurate approach to stress detection in IT professionals. Objective. The project endeavors to create a comprehensive stress detection system by analyzing images, videos, and audio files. This approach enables a deeper understanding of an IT professional's stress levels, capturing nuanced information from multiple data sources. Deep learning models such as Inception ResNet v2, VGG19, CNN, Exception, and ResNet are employed for image and face recognition, while a CNN model is utilized for audio feature analysis. These models excel in pattern recognition, facilitating accurate stress detection. Through image, video, and audio analysis, the project provides a detailed evaluation of stress levels in IT professionals. This multimodal approach enhances accuracy and comprehension of well-being, offering insights into various aspects of stress experienced by individuals. The project implements real-time stress assessment, analyzing facial expressions during live video sessions for immediate stress determination. This capability enables timely interventions, enhancing the effectiveness of stress management strategies and supporting the well-being of IT professionals. Software and hardware requirements. Hardware requirements of the project are operating system of Windows, processor of i5 and above, RAM of 8 GB and above, hard disk of 25 GB and above. Software requirements of the project are application is Anaconda, primary language is Python, front-end framework is Flask, back-end framework is Jupyter Notebook, database is SQLite 3, front-end technologies used in the project are HTML, CSS, JavaScript, and Bootstrap 4.
Working modules or flow of work. To implement this project, we have designed the following modules. The first module is importing libraries. In this module, essential Python libraries are imported to facilitate various tasks throughout the project. TensorFlow is utilized for implementing deep learning algorithms, while OpenCV is employed for image and video processing tasks. NumPy is used for numerical operations and array manipulation, providing efficient data handling capabilities. Additionally, other libraries are imported for tasks such as data visualization, data pre-processing, and model evaluation. Importing datasets. This module involves importing datasets containing audio recordings of emotions from diverse sources such as SAVE, TESS, RAVDIS, and CREMA. These data sets offer a wide range of emotional expressions and variations in speech, serving as valuable resources for training and testing the stress detection model. Each data set have unique characteristics, including the number of samples, emotions represented, and recording conditions, necessitating careful handling during data pre-processing. Exploratory data analysis. In this module, the imported data sets are thoroughly explored to gain insights into their structure, distribution, and characteristics. Exploratory data analysis techniques such as statistical summaries, data profiling, and correlation analysis are employed to understand the relationships between different variables and identify potential patterns or anomalies in the data. Data visualization. Data visualization techniques, including histograms, box plots, and scatter plots, are utilized to visually represent the data and uncover hidden insights that may not be apparent from numerical summaries alone. Data augmentation. Data augmentation techniques are applied to increase the diversity and size of the data set, thereby enhancing the robustness and generalization of the trained model. Common data augmentation techniques include random rotations, flips, zooms, and shifts applied to images and videos, as well as time stretching and pitch shifting applied to audio signals. By introducing variations in the input data, data augmentation helps prevent overfitting and improves the model's ability to generalize to unseen data. Feature extraction. In this module, relevant features are extracted from the images, videos, and audio signals to capture essential information for stress detection. For image analysis, features such as texture descriptors, color histograms, and shape characteristics may be extracted. In video analysis, motion features, facial expressions, and temporal dynamics are commonly considered. For audio analysis, features like mel frequency, substral coefficients, spectral features, and pitch contours are extracted. The selection of appropriate features is critical for capturing discriminative information relevant to stress detection while reducing the dimensionality of the input data. Data preparation. The extracted features are pre processed and formatted to prepare the data for training the deep learning model. This involves tasks such as scaling, normalization, or standardization to ensure that all features are on a similar scale. Categorical variables may be encoded using techniques such as one hot encoding or label encoding to make them suitable for model training. Additionally, data splitting techniques such as stratified sampling or cross validation may be employed to divide the dataset into training and testing subsets while preserving class distributions and minimizing bias. Splitting the data into train and test. This module involves splitting the dataset into separate training and testing subsets to evaluate the performance of the trained model. The training set is used to train the model on labeled examples, while the testing set is used to assess the model's performance on unseen data. Training and building the model. In this module, deep learning models such as convolutional neural networks, CNNs, recurrent neural network RNNs, or hybrid architectures are trained using the prepared dataset. The model learns to map the extracted features to the corresponding stress levels or emotional states through an interactive optimization process. During training, the model's parameters are adjusted based on a specified loss function and optimization algorithm to minimize prediction errors and improve performance. Hyperparameter tuning techniques may be applied to optimize the model's architecture and enhance its learning capacity. Performance comparison. This module involves evaluating the trained models using performance metrics such as accuracy, precision recall, and F1 score. Multiple models are trained and compared to identify the most effective approach for stress detection. Statistical test or cross validation techniques may be employed to assess the significance of performance differences between models and select the best performing model for deployment. Class framework with SQLite for sign up and sign in. A web application is developed using the Flask framework to provide user sign up and sign in functionalities. Flask enables the creation of dynamic web pages and RESTful APIs, allowing users to interact with the stress detection system through a user friendly interface. SQLite is employed as a lightweight relational database management system to store user account information securely. User authentication mechanisms such as password hashing and session management are implemented to ensure the security and privacy of user data. User gives input and the given input is pre-processed for prediction. In this module, users provide input data in the form of images, videos, or audio recordings through the front-end interface of the web application. The input data are pre-processed to extract the relevant features using the same techniques applied during the model training phase. Pre-processing steps include resizing images, extracting frames from videos, or applying signal processing techniques to audio recordings to ensure compatibility with the trained model's input requirements. Trained model is used for prediction. The pre-processed input data are fed into the trained deep learning model to predict the stress level of the IT professional. The model generates predictions based on the extracted features, mapping them to corresponding stress levels or emotional states using the learned patterns and relationship encoded in its parameters. Predictions are generated efficiently using optimized inference algorithms, allowing for real time or near real time performance. Final outcome is displayed through front end. The predicted stress level is displayed to the user through the front end interface of the web application. The final outcome includes visualizations, textual summaries, or actionable recommendations based on the predicted stress level. User friendly visualizations such as progress bars, color coded indicators, or graphical representations may be used to communicate the predicted stress level effectively. Now we will know what are the algorithms used for stress detection. For detecting stress in the images, we have used the following algorithms. The first algorithm is Inception ResNet V2. Inception ResNet V2 is a deep convolutional neural network CNN architecture that combines the strengths of the Inception and ResNet architectures. It consists of multiple layers of convolutional and pooling operations followed by fully connected layers. In the project, Inception ResNet V2 is utilized for image analysis, leveraging its ability to extract hierarchical features from images effectively. It can capture intricate patterns and details in images, which is crucial for identifying visual cues indicative of stress in IT professionals. Coming to the next algorithm, which is VGG19. VGG19 is another deep CNN architecture known for its simplicity and effectiveness. It consists of 19 layers, including convolutional and pooling layers, followed by fully connected layers. VGG19 is widely used in image recognition tasks due to its capability to learn complex patterns and representations from images. In the project, VGG19 is employed for image analysis to extract features from images of IT professionals, aiding in stress detection by identifying visual cues associated with stress. CNN, Convolutional Neural Network. CNN is a class of deep learning architectures specifically designed for image analysis tasks. It consists of multiple layers, including convolutional, pooling, and fully connected layers, which learn hierarchical representations of images. CNNs excel at capturing spatial dependencies and local patterns in images, making them suitable for tasks such as object recognition, classification, and segmentation. In the project, CNNs are used for both image and video analysis to extract features from visual data, enabling accurate detection of stress related cues. Exception. Exception is an advanced CNN architecture that extends the idea of inception modules by replacing standard convolutional layers with depthwise separable convolutions. This architecture aims to capture spatial dependencies and patterns more efficiently while reducing the number of parameters and computational complexity. Exception is particularly well suited for tasks requiring high accuracy and efficiency in image analysis. In the project, exception is utilized for image analysis to extract features from images of IT professionals, contributing to the accurate detection of stress levels through visual cues. The algorithms used to detect stress through audio are CNN, Convolutional Neural Network. CNN architecture is applied to analyze audio signals for stress detection. By processing spectrograms or other audio representations, the CNN learns to extract relevant features such as pitch and intensity, allowing it to identify patterns indicative of stress levels in IT professionals. Trained on a dataset containing audio recordings, the CNN enables the project to incorporate audio data alongside images and videos, providing a comprehensive assessment of stress levels for enhanced accuracy and effectiveness in stress detection. For detecting stress through live video streaming, we have used the following algorithms, which is ResNet, Residual Neural Network. ResNet is a deep learning architecture renowned for its ability to train very deep neural networks effectively by introducing residual connections. These connections enable the model to learn residual mappings, which helps mitigate the vanishing gradient problem and allows for training of deeper networks. In the project, ResNet is utilized for face recognition and analysis tasks, particularly in identifying and analyzing facial expressions of IT professionals. Its capability to capture intricate facial features aids in stress detection by discerning subtle facial cues associated with stress. CNN, Convolutional Neural Network. CNN is a class of deep learning architecture tailored for image analysis tasks. Comprising convolutional, pooling, and fully connected layers, CNNs learns hierarchical representations of images, making them adept at capturing spatial dependencies and local patterns. In the project, CNNs are employed for face analysis, extracting features from facial images to identify facial expressions indicative of stress in IT professionals. Their ability to discern complex patterns enables accurate stress detection by analyzing facial cues associated with stress. Comparison graphs offer a visual breakdown of how our models perform across essential evaluation metrics. Models are compared with the evaluation metrics accuracy, precision, recall, and FN score. This is the accuracy comparison graph for image detection. Here on the x-axis we have algorithm name and on the y-axis we have accuracy score. Accuracy is a measure of the overall correctness of a classification model. It calculates the ratio of correctly predicted instances, both true positive and true negative, to the total number of instances. This is the precision comparison graph. Here on the x-axis, we have algorithm name, and on the y-axis, we have precision score. Precision is a metric that assesses the accuracy of positive predictions made by the model. It calculates the ratio of true positives, correctly predicted positive instances, to the total number of positive predictions, true positives plus false positives. This is recall comparison graph. Here on the x-axis we have algorithm name and on the y-axis we have recall score. Recall, also known as sensitivity or true positive rate, measures the model's ability to correctly identify all relevant instances in the dataset. It calculates the ratio of true positives to the total number of actual positive instances, true positives plus false negatives. This is F1 comparison graph. Here on the x-axis we have algorithm name and on the y-axis we have F1 score. FN score is the harmonic mean of precision and recall. It is a balanced measure that considers both false positives and false negatives. It is calculated as 2 times the product of precision and recall divided by the sum of precision and recall. It provides a single metric that balances precision and recall, making it useful when we want to consider both false positives and false negatives in the evaluation. The algorithm which is performing best in all the evaluation metrics will be used for prediction. Comparison graph for face detection. This is the accuracy comparison graph. This is the precision comparison graph. And these are the comparison graphs of recall and FN score. Execution. To execute this project, first we need to open the code folder which contains the project source code files. This is the code folder. This is the dataset folder. This dataset contains recordings of emotions from diverse sources such as Crema, Ravdis, SAFE, and TESS. These datasets offer a wide range of emotional expressions and variations in speech. This is static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. This is templates folder. This folder contains all the HTML pages used in the project. It includes files like index.html, about.html, and more which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. These are notebook.ipynb files. These are Jupyter Notebook files which contain a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for data science. This is signup.db file. This file is the database file used to store user information. First, we need to copy the path of the code folder from the address bar of the file explorer. Here, I'm copying the path. Now open the Anaconda prompt. Use the cd command followed by a space and paste the copied path and hit enter. This command is used to change the current directory to the code folder's path. Compile the app.py file using the command python space app.py. So here I'm typing python space app.py and hit enter. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address, which is this localhost, and port, which is this. Now copy this local link provided by the Flask framework. I'm copying the link and paste this copied link into any web browser. I usually prefer Google Chrome and hit enter. The homepage of the project is displayed in the browser. This is the front end built using Flask framework. If we are new users, we need to register first. So click on sign up link here. Here we need to enter all these details to register. But I have already registered, so click on sign in button here. Here we need to enter the username and the password which we have registered, and then click on login button here. We have logged in successfully and we are redirected to the prediction page. We will detect stress in IT professionals using different data modalities such as images, video, and audio features. First, we will do the detection through images. So click on images here. Here, we need to upload the images of IT professionals and the application will predict whether that employee is having stress or not. Click on choose file to select the images. So here, I'm selecting the fifth image. Now click on upload button. So here we can see that the employee is having stress. Click on try again. Let us upload some more images. Click on choose file. I'm selecting the first image. So here we can see that this employee is having no stress. Click on try again. Click on choose file. So here we can see that this employee is having stress. In this way, just by uploading the images, we can predict whether the employee is having stress or not. Click on try again. Now we will detect stress through live video streaming. Click on video. Upon clicking the video button, the webcam activates, initiating live detection, where the application detects stress using the trained algorithms. So here we can see that the webcam is activated and the application detects my face using a blue color bounding box, and on top of the bounding box we can see that I'm having stress. Now we will detect with other employees. So here the application has detected another employee's face with the blue color bounding box, and on top of the bounding box we can see that this employee is having no stress. Now we will do the detection with another employee, whether that employee is having stress or not. So here the application has detected one more employee's face with the blue color bounding box, and on top of the bounding box we can see that this employee is having stress. Similarly, the application can detect stress in multiple employees. Now close the camera. Now we will detect stress through audio files. Click on audio. Here we need to upload the audio files of IT professionals, and after uploading the audio files, the application will predict whether the employees are having stress or not. Click on choose file. So here I'm selecting the first audio. Click on upload button. So here we can see stress sample detected. It means that the employee is having the stress. Click on try again. Click on audio. Let us upload some more audio files. Click on choose file. I'm selecting the sixth audio. So here we can see that this employee is having no stress. That is, no stress sample detected. Click on try again. Click on audio. Click on choose file. So here I'm uploading the eighth audio. Now click on upload button. So here we can see that this employee is having no stress. In this way, by uploading the audio files of IT professionals, we can predict whether the employee is having stress or not. Click on logout link here. The conclusion of the project is the project demonstrates the feasibility of using a deep learning approach incorporating image analysis, video analysis, and audio feature analysis for detecting stress in IT professionals. By leveraging multiple data modalities, including images, videos, and audio signals, the system achieves a comprehensive assessment of stress levels, enhancing accuracy and effectiveness in stress detection. Through the integration of image, video, and audio analysis techniques, the project offers a holistic approach to monitoring the well being of IT professionals. By capturing nuance cues from various sources, such as facial expressions, vocal tone, and body language, the system provides a more comprehensive understanding of an individual's stress and overall well being. The incorporation of real time analysis capabilities enables the system to provide prompt feedback and interventions to mitigate stress effectively. For example, the system can analyze facial expressions during live video sessions, offering immediate insights into an individual's stress state and enabling timely interventions to support stress management strategies. The utilization of deep learning algorithms trained on large dataset ensures robust and reliable stress detection without relying on subjective self-reporting or invasive measurements. This approach enhances the user experience by providing objective evaluations of stress and reducing biases inherent in traditional methods. The project lays the groundwork for scalable and adaptable stress detection system that can be tailored to various industries and settings. By leveraging deep learning techniques and multimodal data analysis, the system can be customized to address the unique stressors and challenges faced by different professional groups, ultimately promoting well being and productivity in the workplace.
Thank you for watching video. For more projects please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.